All right, let's start. So we will now talk about the tensor product of representations. You may wonder hearing that as it has already been introduced in the class, but now I will extend and generalize that. So to begin with, let's assume G1 and G2 are two finite groups. Uh, and suppose that we are having two representations, row 1 and row 2. So we will now consider the direct product of these two groups. So from the representations row 1 and row 2, we are going to construct a new representation of the direct product. So in the following way, that our space on which the representation will take place is the tensor product of V1 and V2. So we will define something, a representation which would be denoted by row 1 tensor row 2 in the following way. For each pair, we will consider the map row 1 G1 tensor row 2 G2. Recall that rho I Gi is an invertible linear map on Vi for every I every I in 1, 2. So therefore, this defines so the rho G1 tensor rho G2 defines an invertible linear map on V1 tensor V2 over the field of complex number. And since each row 1 and 2 are homomorphism from their in view of the usual composition laws of tensor product of linear maps, it follows that this is also homomorphism. So the representation that we have just defined is called the tensor product. Product of row 1 and row 2. Row 1 and row 2. All right. The tensor product of row 1 and row 2. All right. So at this point, I must tell you why in the beginning I said that we are going to extend and generalize what has been discussed in the class earlier on the tensor product of representations. So please note the following, that in the very special case when G1 equal to G2 equal to some fixed finite group G, and if I have a representation row of yeah, I have suppose I have representations row 1 on V1, and I have and also another representation of the same group on V2, then from the general definition for any group G1 and G2, from that we get the tensor product representation of G direct product G, V1, V2. Okay, we consider tensor product row 1, tensor row 2. That's how we get a tensor product of G1, G direct product G. Now observe that this contains a subgroup which is isomorphic to G, and namely the diagonal group the diagonal subgroup of G cross G. You can immediately see it is isomorphic to G, and the isomorphism is also the most obvious one. each pair G comma G goes to G. So since this is isomorphic to G, so we can identify the diagonal subgroup with G by this map. That is, we may identify G with the pair G comma G. Now what we do is, in order to see the connection of what we are doing now with what we have seen earlier, we will restrict this representation on this diagonal subgroup, which is already, as I said, being isomorphic to G, has been identified with G. So based on this identification, we get the following map that each so remember, I'm just restricting this homomorphism to diagonal subgroup and then identifying that with G. So that leads me to, so each G goes to rho 1 G tensor rho 2 G. So this is exactly what we have initially defined in one of the earlier classes. So thus you can see by restrict when G1 equal to G2, when G1 equal to G2, then restricting the tensor product on the diagonal subgroup, and the restriction of the as I said, the restriction of the tensor product on the diagonal subgroup coincides with the earlier definition of tensor product of two representations of a group G. Okay, now it is clear why we are saying that it's an extension and generalization. All right, so next what we are going to deal with is the decomposition of tensor product of two representations into irreducible ones. So the natural question that you can ask is, suppose I know all the irreducible representations of G1 and similarly for G2, then using that, can we decompose a representation of G1 direct product G2? So the following theorem gives a complete answer. Okay. So the theorem that we are going to prove, we will do it step by step. So we'll do step by step. Basically, what we want to prove, which is very natural to expect, is suppose I have suppose rho 1 is an irreducible representation of G1 and rho 2 is another irreducible representation of G2. Then this tensor product of these two irreducible representations is an irreducible representation of G1 tensor G2. That is what we will prove. And once we have done this, then you know that how to decompose the tensor, how to decompose a representation of G1 direct tensor representation of G1 direct product G2, because you have all characters of the direct product. Okay, so what we will show is the following, that suppose well, so before that, before stating the theorem, let's observe one thing which is very obvious, that suppose the character of rho 1 is chi1 and here it is chi2, then this tensor product has character chi1 and the tensor product has the character chi1. Tensor product has the character chi1 into chi2, because you know the trace of tensor product is nothing but the product of the individual traces. Okay. So what we will prove now is the following, that suppose chi1 is an irreducible character, chi is an irreducible character of Gi, then so let's yeah, I gen chi I. Well, I think I should choose proper notations that will make the things simpler to see. So yeah, so suppose that chi1 1 and chi1 chi k1 are the irreducible characters of G1, and chi1 chi L are irreducible characters of G2. Then we will now prove that first of all chi I1 times chi J2 is an irreducible character of G1 and G2. So that means the representation corresponding to chi1 tensor product, the representation corresponding to chi2 is going to be irreducible representation of G1 product G2. Okay, now so the first we will prove this, then furthermore we will prove that these are all. So this is the first thing that we are going to prove. The second thing is 1 j I from 1 up to k and j from 1 L are all irreducible character of G1 direct product G2. That's what we will prove. So that shows that from here we can immediately see that irreducible representations of all irreducible representations of the direct product are precisely given by the tensor product of representations, irreducible representations of G1 and irreducible representations of G2. Thus, you have all the irreducible representations of G1 and G2. Now, when using that, since you know all the irreducible representations of the direct product and their characters, from that you can proceed to decompose any given representation of G1 direct G1 direct G1 tensor. You can proceed to decompose any representation of G1 direct product G2. Okay, so let's prove these two statements one by one. We will move to the next page. So first of all, in order to show this is an irreducible character, what we will do is we will prove that this has so if you remember that a character is irreducible if the inner product with itself is 1. Okay, fine. So we will first see this. So basically we have to prove that chi1 1 so chi1 1 G1 and chi2 and chi j 2 G2, this sum G1 G2, we have to prove that this is a this is 1 in order to show that this character is an irreducible one. Okay, fine. Just again to remind you that the way this character is defined is the following, that a point G1 comma G2 the value of the character is that's how the character is defined. Now it is easy to see that this sum is just 1, because first of all you can break this this is just a product, modulus and square. So in particular you can break it as break it like this. Now what you do is you for each g1 in g1 you just take the sum over g2. So for each g1, if you just fix a g1 and then consider all such pairs whose first component is g1, then for each such g1 you encounter a sum like this. So that's how we will see. Now you see that this is 1 because chi j is assumed to be an irreducible character. So therefore this is 1. And now, well, of course, this term is also 1 by the order of g1 cross g2. So it will be 1 by order of g1 times 1 by order of g2. So what you do is, well, let me write it in separately. So here I have this term 1 by order of g1 times 1 by order of g2. But I think now what you have already guessed what to do. So first you push this 1 by order of g2 term inside the summation g2 chi 2 j g2 square. So this gives me 1, and then so with that I have chi I1 g1, then I have the summation, and then further I have g1, right? So this is 1, and now whatever left when this is for if when this is 1, as chi is irreducible, so whatever then we have left with is just this, because this is 1, and that's also 1 because chi is also an irreducible character. So that shows that product of two irreducible characters will remain irreducible. Now the main part is I have to show that these are all irreducible characters. So these are to show that these are all these are all irreducible characters. We'll now show the second one. So our approach would be the following, that if there is another irreducible character, then it has to be orthogonal to all members in this set, right? Because we know that irreducible characters always form an orthogonal basis. So if there is another irreducible character of the direct product, then that has to be orthogonal to all of these bases, all chi I, chi j. So keeping that in mind, we will prove that if a class function is orthogonal to all such things, if a class function is orthogonal to all such things, then the class function has to vanish identically. This is because we know that character is also class functions. If we can prove for general class function, that also goes through for a character. Okay. Now we will assume that f is a class function. F is a class function. F is a class function. Class function of the product. Class function on the product. Class function on the product. And f is orthogonal to all chi I, chi j's. So f g1, g2 is chi I1, g1, chi 2, g2, 2, conjugation and summation. Okay, this is 0. That's what my assumption is. From here I will show f is also 0. And this assumption is for all I and j. Good enough. So what we will do is first fix and chi, fix an I. Next, since we are fixing an I, what we will do is we consider the following map. Let's call it FG2. If the map FG2 is defined as summation G over G1, if G1, G2, chi I1, G1. This is how we define the function G2. It's a function on the group, a function on the group G2. Now you can see that the way it is defined, this is also a class function on G2. Because if you take any conjugation of G2, that applies, so any conjugate of G2, so the second, in the second coordinate the change is happening, but since f is a class function, so it will be the same. All right, so now in view of our assumption that for every I and j this is 0, we see that this f G2, I think this is j, if G2 sum over G2 in G2 is 0 for all ij, right? So for just fix and fix any chi I, then we define this f, which of course depends on the I, but this assumption for all ij that ensures that for this f, for any j, this is 0. Since chi j forms an orthogonal basis of the set of all class functions on G2, so from here it follows that f of G2 is 0 for every G2 in G2. Remember how is f defined? Let's just write how this is defined. FG2 is nothing but G1 in G1 if G1 comma G2 chi I G1, this is 0 for every G2. Now you see this is what we get for any I that we fix in the beginning. Okay, so whatever I fix in the beginning, then write an f accordingly. Maybe if you wish, you can denote this by fi. So finally you get for any I, so for any I you get this fi is identically 0. So thus what you get is this not only holds for a fixed I, it actually holds for any I. Okay, is that clear what I have done? For any I that you fix, you make the function fi, then you see that fi has to be identically 0. So that means, so this is 0 for any I and any v2. Now once that is clear, you know what to do. That you know what to do then. Just again using the same thing, we consider, so fix a G2. Okay, fix G2, we consider this function if G1 comma G2, let's call it phi G1, let's call it phi G1. Of course it depends, since it depends on G2, so let's write it like this. So now this now once we introduce this new function, so the above condition just says that phi g2 of g1 chi I1 g1 conjugate, the sum over g1 is 0 for all I. That ensures. So once this is this, that means you know that again, like earlier, since chi I from the orthogonal base of the set of all class of the space of all class functions, so therefore phi g2 of g1 is so chi g2 of g1 is 0 for every g1, and that's also we get for any, this is what we get for any g2 we start with. So therefore thus we get for every g1 and g2 phi g1 g2, which is defined as f g1 g2 is 0. That is what we are supposed to prove. So therefore that shows every class function which is orthogonal to all these vectors, all these characters, that has to vanish identically. That shows our claim that these are all the irreducible characters of the tensor product of the representations. Tensor product. Sorry, these are all characters of the direct product of the groups G1 and G2. Okay, so with that I will finish. Thank you for your attention. So next time we will talk about some algebraic integers, maybe. Let's see. Okay.